Jules here. Today I'm going to go over a group of G proteins called GABA. GABA is the main inhibitory um, G protein. So let me go ahead and get started. Get my desktop ready here. Let me go through this. Let's see here. Let me turn the sound down some. Great. So let me go ahead and look on here. We're going to go through G proteins. Let's see, how does this work? Nope, I think this is just a message board. Okay, here's over here. All right. Okay. And let me see, is this one? I think this one's larger. Yep. Or is this one larger? Okay, I think I like this one better. Okay, so let's see. Let me look at GABA. Explain how the G protein GABA works. Okay, let me see if we get something simple like that. Okay, so let me give you an overview. So first, there are two major receptors which are classified as G proteins, usually have 7 subunits, and they go through the entire phospholipid bilayer. They transcend the entire phospholipid bilayer, and they usually work together as components to make a very complicated structure known as a G protein. And so GABA there are 2 types of main G proteins that are present in probably every tissue, and that's the main excitatory neurotransmitter GABA, glutamate, and GABA is its opposite. It's the main inhibitory neurotransmitter, GABA. And these two sort of work together to keep the organism in homeostasis, right? So when people get exhausted or fatigued and things like that, usually they have an excess of glutaminergic activity. So they're usually agitated, restless, irritable, and maybe combative. That's that excessive glutaminergic activity. It sort of means that the ship is sort of off balance. And we need to activate GABA, meaning exert more inhibitory tone over the entire organism in order to sort of get the organism balanced. And so we're going to look into the GABA receptor. So here, explain how the G protein GABA works. Okay, G protein activated GABA receptors. Okay. They work by binding to GABA, right? Which is a neurotransmitter, right? Which then activates a G protein. Let me try to keep this one louder because I think the writing may be larger here, so you can see the writing larger. Which then activates a G protein complex that ultimately slows down neuronal activity by inhibiting ion channels that cause excitation, such as voltage-gated calcium channels, activating inhibitory channels like GABA-activated potassium channels. This process reduces the excitability of the postsynaptic neuron, allowing for slower and more relaxed brain processing, and acting as a key inhibitory mechanism for the central nervous system. The key inhibitory mechanism. So let's see the play: glutamate, excitation, GABA inhibition. All right, step-by-step mechanism here. And I think it's important for us to sort of understand the functionality of GABA because when we see a patient who's overly excited or agitated or combative, then we need to know exactly what our targets are. So we're giving this medication and exactly what is it we're targeting. Now remember where the GABA receptors are located. You know, they're located on that mesocortical pathway, right? Mesocortical hyperactivity, positive symptoms of schizophrenia. Of course, we want to target the GABA receptors there to sort of start decreasing the excitability of that mesocortical pathway. Remember the mesolimbic pathway, the reward center, and everything, hyperactivity in that pathway also has GABA receptors, and we can use the GABA receptors to sort of help reduce the excitability in those networks. Also, remember the networks in the basal ganglia, the overexcitation and things like that, and how we can sort of use targeted GABA receptors on those networks. So when we know exactly where the GABA receptors are located and what networks, when we decide on which medication we want to use, we know exactly which pathways we want to hit, right? And so we give the medications, we can titrate the dose upward or downward based upon the clinical effect that we're seeing. And if you know the networks, then you can anticipate what the symptoms are going to be. So here, you look at the step-by-step mechanism. GABA binding. The GABA, the primary inhibitory neurotransmitter, binds to the GABA B receptor on the postsynaptic neuron. So GABA inhibitory neurotransmitter binds to GABA B receptor on the postsynaptic neuron. All right. G protein activation. The binding of GABA to the receptor causes a conformational change in the receptor, which then activates a different G protein, a complex associated with the receptor. This type of G protein has a different subunit than the other ones. Okay. Then the subunit dissociation, two pieces of the unit breaks off and they become active and start chewing, making things. Subunit dissociation, the activated G protein complex dissociates into its component subunits, which is a G protein alpha unit and a beta unit. Right? So you get binding of GABA to the GABA B site, the 3D conformational change. It releases the alpha and gamma subunits. They are released from that complex and then they become active. See what happens next. Okay, cellular modulation. The alpha subunit, this subunit can inhibit adenylyl cyclase, reducing the production of cyclic AMP, which is the CMP, that's the precursor to ATP, which is the energy source, right? Biochemistry, right? The production of cyclic CMP, a common second messenger that promotes cellular excitability. So in here, the alpha subunit inhibits adenylyl cyclase, and this reduces the production of cyclic AMP, which is that precursor to ATP, which is the energy molecule. So if you're decreasing that, then I think it makes it less excitable. That makes sense. Let me see what the beta subunit. Beta subunit, this subunit is known to directly modulate ion channels. Okay, great. It can inhibit voltage-gated calcium channels, and can also activate G proteins activated inward rectifying potassium channels, whatever that is. They come up with new channels all the time. GERK, G protein activated inwardly rectifying potassium channels. You kidding me? That's a name? Okay. So anyway, so the alpha subunit inhibits adenylyl cyclase and reduces cellular activity, and the B channel basically inhibits the ion gated. That makes sense. So it's going to decrease the sensitivity of the ion gated channels, therefore decreasing the degree of depolarization, and therefore the cell isn't that excitable. And then it reduces the total amount of ATP in the cell, the energy source in the cell, by reducing its precursor CAMP, the CAMP right here. Okay, makes sense. Okay, so and these are the two. I guess this is it right here. The mechanism is the alpha adenylate cyclase and the beta. This is the mechanism by which the GABA decreases the inhibitory tone. Okay, next, inhibition of neuronal firing. The combined effect of inhibiting calcium influx and promoting calcium efflux from the cell to a lower rate leads to a slower rate of action potential, slowing down communication between neurons. This here is I think is a very simple example of GABA and its effects. Let me look at the medications and the impact on GABA. So next question, let's see here. Let's see, explain GABA and GABA interaction with alcohol. Okay. Alcohol enhances the brain primary calming neurotransmitter. Let's say inhibitory. Calming. I don't think we use that language in neuropsychiatry. GABA, by increasing its release and boosting the activity of the GABA receptor. So alcohol releases GABA, activates the GABA receptor, slows down brain activity, leading to relaxation and sedation. Alcohol targets GABA. I think it's specifically the B site on GABA. Activate the receptors, slows down brain activity, relaxation, sedation. Chronically, the brain adapts by reducing GABA receptor function, causing tolerance, dependence, and increased excitability during withdrawals, making alcohol use potentially addictive. So let's go through this part here. Chronically, the brain adapts by reducing GABA receptor function, meaning the person has less capabilities of less capable of inhibiting all these impulses over time, causing tolerance, dependence, and increased excitability during drug withdrawals. Okay. What is GABA? Okay, we went through this part here, neurotransmitter, and okay, how alcohol interacts with GABA. Okay, increased GABA activity, and alcohol, particularly alcohol, acts on the GABAergic system in the brain. It increases GABA release. Alcohol can cause more GABA to release from the presynaptic neuron. I was wondering where the GABA came from. It coming from the presynaptic neuron. Enhance GABA A receptor function. Alcohol also binds to the GABA A receptors. I think it's GABA B, causing increase their sensitivity activities. Okay, let me see here. Chronic alcohol consumption. When the alcohol consumption is chronic, the brain adapts to the constant elements of GABAergic transmission. All right, to reduce GABA sensitivity, to counteract the overstimulation, the brain can reduce the number of GABA receptors to decrease their sensitivity to GABA. Yeah, decrease GABA receptors. So overall, you have decreased ability to inhibit things. Withdrawal symptoms. This adaptation can lead to tolerance, needing more alcohol for the same effect, and a state of hyperexcitability once the alcohol is removed, because you've downloaded a significant number of the GABAergic receptors. So now there's an imbalance between glutamate receptors, which is excitatory, and GABAergic receptors, which are inhibitory. So we need to, at times, give medications and things like that to prop up the activity of GABA. Okay, I think that's it there. Okay, and so we're at 16 minutes now. I didn't want to go beyond 20 minutes, but I think you got my point there on GABA. And let me see if anyone has any questions at all. If you have any questions about GABA and alcohol, just let me know. And let me go through some of the questions. Okay, Wade, how you doing, Wade? Hey, buddy, how's it going? All right, Dr. Liv, how's it going? Marianne, hey guys, Nayib, hey guys. Okay, iHash, thank you so much, buddy. What disorders arise when GABA or G protein signal goes wrong? Everything. Everything. The loss of the inhibitory tone. Yeah, so everything. Yeah, yeah, that's a tough question, but everything. Let me see here. Next. How does GABA's effects on G proteins help reduce anxiety and overactivity in the brain? That GABA receptor and the GABA molecule that's released presynaptically results in inhibition, meaning decreased firing of the postsynaptic cell. And so that's its main impact. Decreasing the activity of the postsynaptic cell should reduce anxiety, it should reduce restlessness, it should reduce all the things that are overactive in the brain. Next, okay, thank you. Thank you, Moeen. Appreciate your question. Hey, Umber, how does G protein GABA signaling affect sleep regulation? Overexcitation is basically the networks being overactive, and they really will have to settle down in order for the reticular activation system to sort of start the process of introducing sleep, the structure and the process for sleep. So I think the overactivity basically interferes with that kindling process in the reticular activation system. But I'm not an expert at the reticular activation system. I don't get a chance to deal with it much. I'm on the clinical side where I give them medications, but I think the overstimulation is the reticular activation system doesn't work properly. And thank you so much for your questions. Okay, so we're at 19 minutes and 2 seconds. I wanted to keep this at least under 20 minutes or not. So if you don't have any other questions, I appreciate it. Do. So it's a pleasure talking to you guys. And if you have any other questions, thank you for attending my lecture. And you learn G proteins and you take care. Take care, y'all. Dr. Reed. Ciao. If I had to choose a cortex for my favorite, it would be the prefrontal cortex. Here's the reason why. There's a lot of very important things. And most importantly, they believe the prefrontal cortex is where the ego is located. I think specifically in the right dorsolateral prefrontal cortex, I think, if I can remember it right. But hopefully we'll see it here. And this is a very important part of the human experience. This is the part of the brain that receives the input from the hippocampus, and it assimilates the information and sort of comes up with some type of abstract formulation of what's going on, some abstract reasoning going on. And this prefrontal cortex is very important because it's the seat of your abstract reasoning. So, and if a person is unable to perform operations in that prefrontal cortex, then they may not be able to access abstract reasoning. And now we have two different worlds, a primary concrete world and one that's abstract. And so there are two worlds, concrete and abstract. I think this abstract world is sort of created by this prefrontal cortex and this functioning. So first, let me go ahead and look at, hopefully I don't have to pay for this thing here. Okay, let's see here. Okay. So first, let me see, explain the function of the prefrontal cortex. First, let me go back and show you what the prefrontal cortex looks like. This is it, y'all. So this is the front part of the brain. This is the back part here. This area here is the prefrontal cortex. Now, it's hard to delineate the boundaries of the prefrontal cortex here just by observing the structure of the brain. You have to use sort of probes to sort of electrically probe the areas. And the prefrontal cortex is sort of it's a predominant region where if you stimulate it, it doesn't result in some type of motor activity. So that's one of the ways they try to map out the prefrontal cortex. But we're talking here. So of course, we want to look at the blood supply that goes through there. We want to look at the nerve bundles that goes there. So this is the part we're talking about. Let me see if I can show you maybe a different viewpoint. Okay. Look here. Look at the. Okay. So that's the prefrontal cortex. So let me go here to Grok and here. Okay. Explain the function of the prefrontal cortex. The prefrontal cortex, or PFC, is located at the front of the brain in the frontal lobe, right? Is a critical region responsible for higher order cognitive functionings. That's it. Higher order cognitive functions that distinguish humans from other animals. You know, Grok, it says it clear. It's very clear. The higher order cognitive functioning is to be able to take the, remember the hippocampus gives you declarative, meaning just the facts. It's able to give you the pieces of information, but I believe it's the prefrontal cortex that puts it all together. Let me give you an example of what I'm talking about. Imagine a person in a pit that was so deep that they couldn't climb out of the pit, right? And so you're looking at the cartoon of a man in a pit, and it's too tall for him to get out of the pit. But if you look around the pit, you see pieces of wood. Let's say there's 10 pieces of wood. You look at the pieces of wood and you say, hey, I can put those pieces of wood together to create a ladder, right? The fact that you can see a ladder out of those pieces, that's the higher ordered cognitive functions we're talking about. And that reflects abstract reasoning, because a ladder is more of an abstract concept, particularly if you're stuck in a pit and you're just looking with pieces of wood. And so the solution here for the gentleman who has access to abstract reasoning is that this shouldn't be a major dilemma. I can simply assemble the pieces and climb out of the pit, right? But if the person doesn't have access to this higher order cortical functions, then probably look at the wood and say, hey, it may be a while before I get some help. I may start to use this as firewood. So I may have 10 days to live. I may have 10 days to survive, 10 days worth of firewood down here. Those are two different outcomes and two different realities, two different worlds. So that's what we're talking about, the benefit of this prefrontal cortex, right? So here, but then again, this distinguishes humans from other animals, right? So we get impairment in the prefrontal cortex, and we have some of the behaviors: the hostility, the agitation, aggressiveness, combativeness, the rage. Things that just similarly seen in the animal world, right? It acts as the brain's executive control center, right? Managing complex behavior and decision making. So as you can see, impairment in this lobe can have a significant impact on the person's capacity to behave, right? Here's the breakdown: decision making and problem solving, right? Working memory, this is very important. It temporarily holds and manipulates information, right? This is very important. Impulse control and self regulation, right? Attention and focus, yeah. Planning and organization, social behaviors and empathy, cognitive flexibility. Um, and look here. If you were to look at any of the neuropsych tests or anything like that, they basically cover these areas. Decision makings. The PFCs evaluates options, weighs consequences, and make decisions based on goals and values. Remember when the best decision, less is more. The less you meddle with things, probably the better the outcome will be for you. And I think it has something to do with the decision making and problem solving capacity, because once you start to take time to really process the things around you or the situation around you, you will likely come up on your own with a completely different decision. So this is one of the reasons why acting impulsively or acting without really considering what's happening, while it's so consequential, and how it can be so detrimental to you by simply reacting to things. The Out of the overwhelming majority of the actions that someone takes, if they were to sit down and sort of go through the process of analyzing this situation, they will not likely make any decision about it at all. They will likely walk away as the best solution to the issue. Working memory. Okay, it temporarily holds information and manipulates information, like remembering a phone number. Like remembering a phone number long enough to dial it or keep it on track. Okay. Okay. So working memory, temporary holds and manipulate information. Now, this is very important because and this is why the hippocampus is so important. The hippocampus will receive the information and move it to the prefrontal cortex. And if the working memory capacity is impaired, then the person would not get the information into their brain to even be considered in the first place. So for example, the man in the pit with 10 pieces of wood, this person may only have the capacity to remember 2 or 3 of the 10 pieces. And so when their prefrontal cortex goes to sort of render a solution, it only renders a solution based upon 2 or 3 pieces of information, not on 10 pieces of information. And that's probably one reason why they couldn't figure out that this was actually a ladder in the first place, because this working memory is impaired. So the working memory is very important. Impulse control and self-regulation, right? The PFC inhibits impulse controls and behaviors. Okay. The PFC inhibits impulsive behaviors and regulates emotions. It is why you can resist eating a whole cake or staying calm during a heated argument, right? Attention and focus. It distracts attention to relevant tasks while filtering out distractions. Planning and organization. The PFC enables you to set goals, create strategies, and break task into manageable steps like organizing the project, or scheduling your day. Look, social behavior and empathy. It possesses social cues, helps interpret others' intentions, and guides appropriate social responses. This is key to understanding empathy and navigating social interactions. Yep. Cognitive flexibility. The PFC allows you to adapt to new situations, shifts perspectives, and think creatively. It will help you pivot when a plan fails or consider something else's point of view. So, as you can see, it's very important. This prefrontal cortex is a very important structure here. Let me see if we have any other questions so far. So let's see here. Okay. Hey guys, how's it going? Appreciate your support. Let's see here. How does modern society feed and shape the ego through the brain? In the early developmental process, in the early developmental process, the ego is in the process of being formed. And so the person relies on all of the people around them, particularly the primary caregiver, the family, to help reflect what's happening with them. So early on, we're dependent upon this external component of our ego, which is our society, our culture, our belief systems, serving as an external ego. And that helps us understand what type of boundaries we should have, or limitations we should have, or how we should perceive things. And so that's how society shapes it. Society gives you some type of identity, right? And right now, so identity is basically based upon pigment color, right? And as complex as a human is, you divide all humans based upon pigmentation. Why not group everybody based upon height? Let's see. Yeah. Hey, iHash, how's it going, buddy? Is the ego always negative, or does it serve a protective function? I often give an example of the man who is starving in the desert, starving in the desert and thirsty, right? And he's crawling on his knees and trying to make it through the desert. And all of a sudden he sees an oasis. We know it's a mirage. So he sees a water in front of him. He hears the water. He can feel he get people drinking water, people wasting water, splashing in water everywhere. He sees a mirage, and he sees it there. He believes it there. And if you were to tell him that it's not an illusion, he won't believe you. Why? Because its ego is creating that illusion for him. It's creating it through a process called projection. And it's what happens around all of us all the time. This is a projected world. And so he goes and he continues to sort of keep moving and striving, and he keeps going and crawling. And finally he gets to where the water's supposed to be, and he realizes it's not any water there, right? It was all an illusion, right? However, crawling those extra 2 kilometers may have saved his life, because now he can probably be seen. So in this situation, the ego serves to sort of protect you, but the situations may not be appropriate for how it applies how it applies its remedies. In this case, it made the man believe that there's something that wasn't there, and the man pursued it. You could have said that these were hallucinations or delusions and stuff like that. That's what we would call them. But it's a projection by his ego, and his ego is trying to preserve him and preserve his life. Let's say here, next question here. What are the implications of the development of prefrontal cortex, during the adolescent legally? Okay, so what are the implications of not developing the prefrontal cortex? I don't think there's any legal remedies, but We see that in a lot of cases of abuse. So when you see victims of abuse, particularly victims of narcissistic abuse, the injuries occur particularly in the prefrontal cortex. And if you look at the damage and the damage that the victims of narcissistic abuse or chronic stalking or PTSD have, it has the damage located here in his prefrontal cortex. And so let's look at this. Remember, difficulty making decisions and solving problems, right? Very forgetful, impulse control, rage attacks, anger attacks, confrontational, argumentative. Oh, yeah, I'm still here. Okay. Attention and concentration processing, planning and organizing, social behavior, right? Cognitive flexibility, difficulty working. So the point of narcissistic abuse is to actually control your ego. And one of the ways they control your ego is basically get you to abandon your reality and live in theirs. And anytime you go back into your reality, you're going to have to face the disturbances that they intentionally create from you by interrupting the information in your prefrontal cortex. Who'd have thought they'd be so sneaky as that? These people understand how to disrupt your brain functioning so that you have problems at work, so you have problems with your relationships, where you have problems with your friends, and they destroy all of these things and hope and for you to return back to their world. See, narcissism and all this abuse is about someone forcing you live in their reality under a character that they determine with rules that they've already set for you. And anytime you get out of those rules, particularly leave their reality, meaning put yourself first, then they attack you with these things, right? So that's the prefrontal cortex. Next, let me see let's look at the blood supply. Let's look at the blood supply. Explain the blood supply in the prefrontal cortex. The blood supply to the prefrontal cortex, located in the frontal lobe of the brain, is primarily provided by branches of the anterior cerebral artery and the middle cerebral artery, which are parts of the internal carotid artery system. Remember that bifurcation right there between the common carotid, the internal carotid, and the external carotid? And then all the gook that happens right there at that junction. And so you can get buildup of the cholesterol plaques that narrow the lumen of the arteries. And if you narrow the lumen of the arteries, then you interfere with the blood supply to both the anterior cerebral artery and the middle cerebral artery. And so you want to look at increased cholesterol plaques and then strokes, very high, chronic high blood pressure, hypercholesterolism, diabetes, and things like that as risk factors here. These arteries deliver oxygenated blood to the prefrontal cortex, high metabolic demands due to its role in complex cognitive functioning. Yeah, high metabolic demands. Yeah. Okay, here, let me just, I'm going to show an image of the, I'm going to start at the common carotid and then go up. Let's see here. Do I have it here? Okay, so here is the common carotid artery right here. Now here's the external one here. Here's the internal one. This is the one we're talking about here. Going up here, look at this, going up there. Look at that route. And then here's the distribution here. It'll be in this area, in this region here. Yeah. So this is the internal carotid. So this is one of them. And then the middle cerebral artery, I believe the junction is somewhere around here. Let me, okay, so okay, so, okay, all right. Okay, we saw which one was it we saw? Okay, the common carotid. We turn to internal carotid. Okay, here, okay, anterior cerebral, and let me show these. Okay, so, yep, I showed the internal carotid system there. Now, let me go from the internal carotid system to the, internal carotid. Okay, hopefully I'll see how it breaks off. Okay, so let's see, internal carotid. Okay, we got an internal carotid here, but I want to see how it breaks. I want to see how it bifurcates. All right, and then let's see branches. Well, let me just go ahead and go to middle cerebral artery. Okay. Middle cerebral artery, right? I wish I could show. So the internal carotid would be going into the picture. And I guess when it bifurcates here, it changes. Well, okay, middle cerebral artery, and then so middle cerebral artery, okay, it arises from the internal carotid and travels longitudinally along the Sylvian fissure. It supplies the lateral prefrontal cortex, okay, and the anterior cerebral artery, it originates from the internal carotid artery and runs along the medial surface of the brain. It supplies the medial prefrontal cortex. So the anterior cerebral artery supplies the medial prefrontal cortex, and the medial cerebral artery covers the lateral prefrontal cortex. Okay, sounds good. Venous drainage, I don't think we need to look into that. Microcirculation, I don't think we need to look at that. Okay, circulation. Okay, stroke. Blockage or rupture of the anterior cerebral artery, or MCA, can lead to prefrontal cortex damage, causing cognitive and behavioral problems. Okay. Aneurysm, the anterior ACA is a common site for aneurysm, yeah, which can disrupt the prefrontal cortex. Okay. Techniques, and we can pick it up on an MRI. Okay, so yeah, so that's interesting here. All right, so right now I'm at 26 minutes. Let me just look at the networks, the nerve networks. So let me just look at the networks going through that section, and we're going to look at the receptors on those networks. Okay. Complex stuff. I didn't know I was going to present like this. I was going to look for so this is too in depth. Let me look for the receptors. Okay, guys, back. Okay, so I wanted to at least go show the receptors on that prefrontal cortex, and so at least you would get an idea of the different type of medications we can use to sort of treat the dysfunction in that area. So here, remember the dopamine receptors, D1 and D2. Remember the typical antipsychotics are primarily D2 receptors, whereas the atypical bind both. The atypical also have other receptors like serotonergic receptors here, glutamate receptors here. Remember, the glutamate is the main excitatory neurotransmitter. Sometimes I try to use Namenda as an agent to sort of decrease glutamatergic activity if they seem to be too easily excitable. GABA receptors, and so benzodiazepines may be helpful in terms of inhibiting impulses. So GABA is the major inhibitory neurotransmitters. And of course, you have the interaction between the two. But so, yeah, so dopamine receptors, serotonin, glutamate, and GABA receptors located throughout the prefrontal cortex. I think that's all I wanted to do for today. And if you have any other questions, please put them in the comments and I'll try to get to them if I can. But otherwise, it's a pleasure speaking to everyone. And until then, I'll talk to you guys later. Take care. Read out. Bye now. Today, we're going to have a very interesting topic. It's on the frontal lobe. And the frontal lobe is the seat of your executive function. This is what makes you human, right? This is what makes you the executive, right? And loss of this is a term called executive dysfunction, meaning there doesn't seem to be any purposeful behavior. It's just doing a lot of things, but nothing really meaningful or nothing really purposeful. That's what executive dysfunction is. So let me go ahead and look here. First, let me see if I can go to here. Okay, let me see if I can go to Grok. Ron, how's it going, buddy? My man, Ron, how you doing? Can you hear me, Ron? How's it going, buddy? Okay, so here, first let me show you an image of the frontal lobe. Here it is. Here's the frontal lobe here in red here. And this prefrontal cortex is still a part of this frontal lobe. Here is the temporal lobe here, right? Here's the parietal lobe here. So what we're looking at here, we want to look at the frontal lobe here. Okay? And so let me just here briefly. What does the frontal lobe do? Here. The frontal lobe of the brain is vital to human consciousness, as well as functions that appear uniquely human, such as spoken language. Frontal lobe damage can lead to a wide variety of symptoms: memory, judgment, abstract thought, creativity, social appropriateness, motor tasks. The frontal lobes are the most common injury that occur in the brain. Damage can lead to a wide variety of symptoms such as movement difficulties, difficulty speaking, and changes in social behavior. So here's the frontal lobe here. And one of the reasons why it's important to sort of understand this part of the brain is that when you start to see individuals with behavioral problems, like problems with judgment or things like that, problems with insight, problems with organization, you want to think about the frontal lobe. And in cases with frontal lobe hypoactivity, that's usually seen in cases of attention deficit disorder, right? And remember, we place those patients on a stimulant, right? So if they're hyperactive and restless and can't sit down because attention deficit hyperactivity disorder, then why do you put them on a stimulant? Well, you want to stimulate this frontal lobe here. So the stimulant is not for the body, it's to stimulate the frontal lobe. The frontal lobe becomes more active, more dominant, and then the frontal lobe begin to suppress all the activity that you see, the excessive motor activity and things like that that you see in patients with attention deficit hyperactivity disorder. So you can see how important this frontal lobe is, and how important it is to know what the function is. So here, so explain the function of the frontal lobe. So in this series, remember we looked at the hippocampus and we sort of looked at how those systems were functioning in there. Then we went to the amygdala. I remember that we did the basal ganglia. And remember, in each one of these systems, we want to look at the networking and look at the receptor profiles in here. And hopefully, if we understood the receptors, then we sort of have an idea of what type of medications we want to sort of address issues connected with dysfunction in the frontal lobe. Okay. So here, the frontal lobe, located in the front of the brain, is a critical region responsible for a wide range of higher order cognitive and behavioral functions. It plays a central role in what makes us uniquely human, including decision making, planning, and personality expression. Below is a concise explanation of its primary functions with deeper reasoning where relevant. Okay, so look at this. So executive function and decision making, right? Motor control, remember ADHD, speech and language production, hyperactivity, that talky, personality and social behavior, attention and working memory, emotional regulation, so all of these are very important roles of the frontal lobe. So here, so executive function and decision making. The frontal lobe, particularly the prefrontal cortex, is responsible for executive functions, which include problem solving, right? Reasoning, right? Planning, right? Decision making. It evaluates options, weighs consequences, and help prioritize actions based upon goals. As you can see, that's a very important function to have. Very important function: problem solving, reasoning, planning, decision making. Okay, here, motor control. The primary motor cortex, located in the posterior part of the frontal lobes, along the precentral gyrus, controls voluntary muscle movement. It sends signals to muscles throughout the body to execute precise actions when writing or while walking. So we have the primary motor cortex that's located in the frontal lobe. Controls voluntary muscle movements, So I'm sure you get the stimulants make the frontal lobe more active, so you get more control over the movements. And I guess that's the mechanism of shutting down the hyperactivity seen in attention deficit disorder. Okay, the motor cortex is organized somatotopically. That is the motor homunculus. Remember the homunculus, where specific areas correspond to specific body parts, ensuring coordinated and intentional movements. And so, so here, this frontal lobe, executive functioning and motor control. Okay, speech and language. Yep, Broca's areas. Yeah, typically, it's been a while since I've pronounced Broca's areas. I even thought about this. Broca's areas, typically located in the left frontal lobe, is crucial for speech production and language production. It coordinates the muscles involved in speaking and helps form coherent sentences. It helps coordinate the muscles involved in speaking and helps form coherent sentences. Broca's area. Remember, Broca's aphasia. When we have, Broca's area, Broca's aphasia. Okay, yeah, damage to this area can result in Broca's aphasia, where individuals struggle to produce fluent speech, but still may understand language. So they can receive the information, but they simply have difficulty with the process of speaking due to the damage. Okay, personality and social behavior. The frontal lobe, especially the orbital frontal cortex, regulates personality traits, emotional responses, and social behaviors. It helps us interpret social cues, inhibit inappropriate actions, and exhibit empathy. For instance, it prevents impulsive or socially unacceptable behaviors like shouting in a quiet setting by assessing context and consequences. That makes sense. Okay. Attention and working memory. Yeah, for attention deficit disorder, right? The frontal lobe helps maintain focus and damage working memory and manage. The frontal lobe helps maintain focus and manage working memory, the ability to hold and manipulate information temporarily. Yeah. It filters distractions and sustain attentions on task, which is why frontal lobe dysfunction is also linked to conditions such as ADHD. Yeah, like we said before, uh, attention and working memory. This is significant. Yeah, because I thought part of the working memory was also in the prefrontal cortex also. So I can see the attention and working memory, social behaviors, Broca's aphasia, motor control, ADHD, of course, executive dysfunction. Um, so here, emotional regulation. The prefrontal cortex interacts with the limbic system. I can imagine, yeah, yeah, to modulate emotions. To modulate emotion. It helps balance emotional impulses with rational thoughts, enabling us to stay calm under stress or delay gratification. For example, choosing to study instead of watching TV involves the frontal lobe suppressing immediate desires for a long term goal. Yeah, yeah. For example, choosing to study instead of watching TV involves the frontal lobe suppressing immediate desires for long term goals. Huh, amazing. The frontal lobe is one of the last brain regions to fully mature. Yeah. Not often until the mid 20s, which explains why adolescents may struggle with impulse control or long term planning. Yeah. Why they need so much support and structure. Damage to the frontal lobes via trauma, strokes, or neurodegenerative diseases can lead to impairment in poor decision making, apathy, or disinhibition, depending on the affected subregions. Yeah, we see that a lot in diffuse traumatic brain injuries and things like that. Damage to the frontal lobe. You see the impulsivity, the agitation, combativeness, aggressiveness, the unpredictable nature of it all. Um, yeah, its connectivity with other brain regions like the limbic system and the parietal lobe allows it to integrate sensory, emotional, and cognitive information for cohesive behavioral experience. And so this is really interesting on the frontal lobe here. Um, so also, let me see if it can explain the networks going through the frontal lobe. Can explain operating in frontal lobe. The frontal parietal network, the default node network, the Salence network. Yep. I'm not sure if this is going to be what you guys are interested in as medical students, things like that. Oh, it's giving all the networks. Okay, here, the frontal lobe is an integral to multiple neural networks, each specialized for distinct functions. The PN for cognitive control, the DNV for self-reflection, the SN for salience detections, CON for sustained attention, the frontal striatal for reward and habit, motor network for movement, and language network for speech. I wanted to point out that they did go through the process of sort of labeling these huge networks that sort of helps these lobes function like this. So let me just go through a few of them just to show you, but not too much. This frontal parietal network. It is critical for high levels of cognitive functioning, including working memory, problem solving, planning, and cognitive control. Okay, look at this. Oh, how it works. The FPN integrates information from sensory and memory systems to guide goal-directed behavior. Okay, and the default mode network. It involves the DMV is involved in internally focused process such as self-reflection, mind wandering, autobiographical memory, and image future scenarios. And so I just wanted to show you that. Didn't want to get too deep into it, but also let me go through and see if they can describe the receptor profiles. The receptor profiles in the frontal lobe. And remember, we covered the amygdala yesterday. And remember, we're looking at the different receptors. I'm sure it's the same group of receptors: glutamate, GABA, dopamine, right? Serotonin, norepinephrine. The frontal lobe, a critical region for cognitive, emotional, and motor, right? So cognitive, emotional, motor functions contain a diverse array of neurotransmitter receptors that mediate neuronal communications and modulate network activity. These receptor profiles determine how neurons in the frontal lobe respond to neurotransmitters, right? Drugs and other signaling molecules influencing the function, right? So we want to look at the receptors. And so at least if you understand the receptors in this region, at least you understand what medications you can reach for. Remember, so we have our glutamate receptors. You know, we have one of the medications I use to target glutamate is Namenda. And so it decreases glutaminergic activity. That's very helpful in patients I use with agitation. We have GABA receptors, typically benzodiazepines, right? We can use to sort of help with any agitation and combativeness there. And remember, for glutamate and GABA, these are the main. Glutamate is the main excitatory neurotransmitter. GABA is the main inhibitory neurotransmitter. And you want to get balance between both. Remember, the major the major mood stabilizers like Depakote and lithium results in down regulation of glutamate receptors and upregulation of GABA receptor. So remember, with chronic agitation, combativeness, maybe head injuries, with impulsivities, restlessness, and things like that, you really want to make sure that you can use your mood stabilizers to target both the glutamate here and the GABA receptors all in one here. So I think this is one of the reasons why Depakote and lithium are very effective in diffuse traumatic brain injuries, particularly ones that may involve the frontal lobe. So here are glutamate receptors, GABA receptors. So GABA, the major mood stabilizers, and also benzodiazepines, IM benzodiazepines. Okay, now dopamine receptors. Okay, so it has D1 receptors, right? And then it has also D2 receptors, D2-like receptors. Remember, for the typical antipsychotics, they primarily bind D2 receptors, not necessarily D1 receptors. So they have a very high affinity for these receptors. So they bind them very strongly. That's the typical antipsychotics. Now remember, the atypical antipsychotics also, they bind D1 receptors, D2 receptors, and also serotonin receptors, norepinephrine receptors, either acetylcholine receptors too. So, so in this case, a mood stabilizer can help downregulate glutamate receptors, upregulate GABA receptors. And if it's an urgency, you can use benzodiazepines urgently to target GABA to activate those receptors to get the inhibitory benefits. With a typical antipsychotic, you'll target the D2 receptor here, but you won't target any of the other receptors. If you were to use a atypical antipsychotics, it'll target D1 receptors, D2 receptors, the serotonergic receptors. Some of them target the acetylcholine receptors. So that's why mood stabilizers like Depakote lithium and atypical antipsychotics like Seroquel, Risperdal, Geodon are very helpful in things like diffuse traumatic brain injuries. Does that make sense, guys? Hope so. Let me see here. Let me see if I can get any questions here. I'm here at 20 minutes, and so I didn't want to go too far over 20 minutes. I didn't want these little sessions to be too long, but let me see if I can answer one question. Hey, Mohammed, how's it going, buddy? Thanks for the question, Mohammed. Is the frontal lobe the true seat of free will? I would say absolutely. That's where you decide to turn left or to turn right, and that's the ultimate decisions. Okay. All right, guys, I think that's it for today. I hope that was helpful for you guys. If you have any questions, you can just put them in the comment section. And so this is on the frontal lobe. I hope it's helpful for you guys. Take care, guys. Read out. Ciao.